said I must make it to the class, right? So actually glad that how far we've come, right? And I'm glad that we're making progress so far, so good, right? And for me, it's an emotional moment. I don't know for others. Even my prayers that the Lord will crown our efforts with joy. You know that moment when you've done everything that you know how to do, and then you are now telling God, Baba, please do this for us, right? So that's the situation I am currently, asking the Lord to show us mercy, and that there's nothing to panic about anyway. But then it's more like people that are playing Champions League. You are at the final round, so that fear can be there actually. But then we just have to do what we have to do. So this topic have been in my mind, and I said if I don't teach this, then my spirit will not be at peace. That's why I have to find a way to do this. If you notice, I couldn't prepare the slide as always because I didn't have the time to do that. But hopefully, this will help us. All right, so let's get started. So today we'll be looking at current, electricity, and the likes of it, right? So today we'll look at three key things. We're going to look at electric current. We're going to look at, let me just write them down. This is going to be a very stressful one for me today because I prefer preparing the slides and then using class time to teach. But as it stands now, we're going to do both of them, right? So we're looking at electric current. Under electric current, we look at um, the definition. What does it entail? Look at columns, right? Look at the measurement, and then we look at potential difference. I think resistance happens to be the biggest. So for this potential difference, we'll look at the terminal PD. We'll also look at the EMF PD, right? Terminal PD and your EMF. These are the key things you're going to look at potential difference. But the key guy now is your electric resistance. Under electric resistance, this is where we look at resistivity. This is where we look at the kinds of resistors in series, in parallel. We look at variable resistors like a rheostat. We look at your standard resistor, which is also called the known resistors. We look at when resistors are in series, when they're in parallel. We look at how you can measure resistance, right? We look at the Wheatstone bridge. We look at the meter bridge. There's another one as well. All of those things are key things we're going to be looking at for today, right? How to measure the resistance. We also look at internal resistance and the relationship between your potential, what do you call it? Your terminal PD and your EMF. So a lot of things to learn today, and hopefully I've told Paul already to get questions for us. I'm hoping that he's going to come to class before we start solving these questions. All right, so the first one on the list is your electric current. Now, electric current simply the quantity of charge flowing through, right, a circuit per second, right, and it's measured in coulomb. So when you talk about electric current, I think I should just use my normal pattern. So electric current. So for electric current, we'll consider two key things, right? We'll look at the first one. It is simply what your quantity of charge. Quantity of charge. I just feel like not writing, right? I just feel like talking because it's usually stressful to do all the writing and writing and writing, but then we just have to do that. So electric current has to do with the quantity of charge. Quantity of charge over second, you know that already. So we have the quantity of charge. Which is measured in coulomb, right? Coulombs, right? Measured in coulombs. Am I spelling this coulomb very well? All over what? The time that will be in seconds. Time in seconds. And there are key things I highlighted here for quantity of charge. I think I'm not spelling these columns properly. It should be CO, right? It should just be CO. But I know you know what I'm talking about. Right, time in seconds. So now you know that electric current is measured in ampere. I'm going to be very fast with this guy, right? So I is in ampere as much as we can. So I is in ampere. I'm going to be very, very fast. I is in ampere. Now, if you start seeing things like milliampere, microampere, this is where I want you to also take notes. So you have something like 1 milliampere, you have 1 microampere, Always remember that they're talking about 10 raised power minus 3 ampere. And also they are talking about what 10 raised power minus 6 ampere. All right. So in case you see things along this line, take note of that. So what are the instruments for measuring electric current? We make use of galvanometer. However, galvanometer is used to just test it, like to dictate electric current, not test it. The right way to use it is to detect. So we use galvanometer to do what? To dictate electric current. That's the essence of your galvanometer, just to detect electric current, right? So you don't use that galvanometer to measure large quantity of electricity, hence you blow it up, just to dictate electric current. Why? To measure the exact amount of electric current, we make use of what? Your ammeter, right? So ammeter is used to measure the exact amount of electric current. All right. So in terms of the measurements, in terms of the instruments, I would say that we make use of what? The instruments. I wish I would not be writing that. You guys should just be taking notes. But then it's not possible. So for the instruments, we make use of what? We'll have your galvanometer. I think I spoke about galvanometer the last time. We'll have the galvanometer, and then we'll have the ammeter. So now the key difference between the both of them, remember what I said? This one measures the exact amount, right? Measures exact amount of current. Of current flowing in the circuit. So this is used to dictate small amount of current. All right, so I think that said, we'll have the two key instruments that we'll make use of for this. Now, another key thing is that in a circuit, we always connect the ammeter in series. All right, we'll connect it in series. Why do we connect it in series? So we can measure the exact amount of current flowing through the circuit. So it is expected at every point in time, like the standard is that the ammeter should be connected in series. That doesn't mean that in every circuit we'll connect the ammeter in series, but then it is important to know that we must always connect it in series. So we can actually measure the current flowing directly, right? So we must always connect that guy in series. Take note of that, what I just said. All right, ammeter always connected what in series. Should I put that down? All right, so note by that ammeter connected in series. In series to do what? This is taking time. All right, so that's the statement I can make about your current. So the next one now, but remember we can have parallel and series connection, right? And when the connection and is are in series, same amount of current will flow through each of the ammeters connected in series. But when the connections are in parallel, the current is going to be different. Very important statement I just made. When the connections are in series, it is expected that what happens? That the current flowing through the ammeters are going to be the same when the connections are in series. And that's why it's always recommended that we connect the ammeters in series. But if they are connected in parallel, it is expedient to know that the currents are going to be what different. All right. So I said that what ammeter must always be connected in series to be able to measure the flow of current directly through the circuit. So that is all for current. And I've mentioned something very key there when the connections are in series. All right. So in series now, let me just set a diagram. All right. So in series, let's assume we'll have something this way. Then we have Let's say we'll have our battery this way. Then we'll have ammeter here. Let's say here is A. Sorry. Yeah, this is your ammeter A here. Let's have our bulb right here. You know the symbol for bulb, isn't it? Bulb is usually like this, right? Then let's say we have another ammeter down here. You can see that the connections are in series. Please, that's what I want you to pay attention to. All right, so let's close it up right here. Let's close it up right here. So the current here, they are going to be what? The same current flowing through them. So let's assume that what we have here is I. That same I will flow through here, right? That same I is going to flow through here. All right. So in connections in series, the same amount of current is going to what? Flow through. It's important to note that the sign for your galvanometer, if you see something this way, right, it just has a line this way. This is your galvanometer. That's the symbol for galvanometer. When you have A inside, is your ammeter, and I believe all of us are aware of this. All right. So the next one now is your potential difference. All right, is your potential difference. Potential difference is just like pressure difference between 2 points. But this time around, you are dealing with what? You are dealing with electric current. All right. So what comes to my mind when I talk about potential difference, all right, is more like the work done when one coulomb of charge flows from one point to another. The work done. Potential difference is the work done when one coulomb flows from one point of the circuit to another point, right? And the instrument we use in measurement is your voltmeter, right? So we'll make use of the voltmeter for the measurement. Remember, I've spoken about electric current, and I've said key things about electric current, always connecting them in series. When we look at your voltmeter, you will see that we always connect our voltmeter in parallel. All of these things will not make sense when we start talking about resistance. Have you seen a question where they say you have a bulb connected in series? What happens? What do you do to ensure that the bulbs get dimmer? I think there are questions like that. What happens to the bulb? You now have a particular set of a bulb, and as the current is flowing, the bulb is getting dimmer. What kind of connection is that? Have you seen that kind of question before? Anybody? Have you never answered past question? Where they tell that the bulb gets dimmer, exactly, yeah. So there are questions that way, is your ability to know when they are in series and when they are in parallel. All right, that said, let's talk about your potential difference. Now, for the potential difference, like I rightly said, is more like pressure difference between 2 points. All right, but for your electricity, we take it as the work done, right, in moving what? When one coulomb of charge is moved from one point to another, movement of one coulomb of charge. I want to be extremely fast so that we can meet up with everything we have under this electricity as fast as possible. All right, should I write that definition? So in brackets, this is PD. So I said that PD between 2 points, between any 2 points is the work done between any 2 points is the work done. So in case you have that in your question, is the work done in a circuit, work done in a circuit, when one coulomb of charge moves, when it moves from one point to another. All right, so that's your potential difference, and we measure this potential difference using what? Your voltmeter. So PD, in terms of measurement, we use our what? Our voltmeter. Is it voltmeter or voltmeter? Which one? Voltmeter, which one? Science students. What do we call it? Titi and the rest. Emmanuel also. Is it voltmeter or voltmeter? Anyone you call it. All right. So we use okay. The voltmeter is usually across 2 points where the PD is required, and it's usually connected in parallel, right? Voltmeter is always connected between those 2 points that you want to get the potential difference. Remember, it says the work done between 2 points. So the voltmeter connected between 2 points, and is always connected in parallel across those 2 points. Ameta series, this one parallel. All right. So that said, um, mm, now what happens if I connect the voltmeter in series? Because the voltmeter is a very high resistance instrument or equipment. What happens is that it's going to reduce the amount of current flowing through. That is why we don't place the voltmeter in parallel. Once it's in parallel, in series, what will happen is that no measurable current will flow. Current is not going to flow from that very circuit because your voltmeter on its own is a high resistance instrument. You know, the higher the resistance, the lower the current that can flow through. Right? When something is a conductor, it has high resistance, which means current can easily, low resistance, I mean to say, current can easily flow through. But when I'm a poor conductor, which means that my resistance is high, and current cannot easily flow through me. That is why we don't place this guy in series in a particular circuit because it's going to what resist the flow of current in that circuit. Hope that makes sense now. Why the voltmeter is always connected in parallel between 2 points. Now, voltmeter connected across how many points? Across 2 points. Across 2 points where the PD across the 2 points where the PD is required. That is to say that it is connected in parallel. It is connected in parallel. It is connected in parallel. All right, so that being said, and I've made the statement why it is always connected in parallel, so there's no need of putting it here. So the next one is your EMF and your terminal PD. I think I should talk about this terminal PD when I talk about resistance actually. So let me go to resistance. When I get to resistance, I cannot talk about terminal PD because terminal PD has to do with what? When the circuit is closed, right? The potential difference in an external circuit when the circuit is closed. I believe we know what a closed circuit is and what an open circuit is, right? Just like in your house, when your switch is off, that is an open circuit. Until you turn it on, that is when current is going to flow, right? So that is what your terminal PD revolves around. But this time around, it is making reference to a battery. You know, in secondary school, made use of battery, but you can remember that there's never a time we did that experiment with just one battery. We bring together different cells, right? And it's a group of those cells that make up the battery. Sometimes we tie it with this black tape, right? I believe each and every one of us did our experiment on electricity. I'm assuming that we did, right? So now, that time when you put, if you've ever seen a key before, give me a thumbs up. Experiment, that key that will plug in. How many persons have seen that? You remove the key, you plug the key. Nobody. Quite unfortunate. Okay, Mesho gave me a thumbs up. No other person here. Wow. My God. You guys didn't do experiments in electricity? How did he pass WIAC? All right. For me, we did a lot of experiments in electricity, a whole lot of them, right? We plug in the key, remove the key, the current will flow. So your key is more like your circuit. All right, that's for your potential difference anyway. Now let's talk about your resistance, which is another key guy, and this is where we spend most of our time. We were given options. Options like what?
Yeah, so they gave us prism, they gave us
Mm-hmm.
electricity, they gave us one other one like this. So you have to pick two, and I
Yeah,
picked prism. I didn't pick
but
electricity first. It was
but
crazy.
even at that, during the time, from my own time, we did a lot of experiments, right? In as much as you pick the one you're going to answer in exam, I can remember that we picked simple harmonic motion and
Yes,
electricity.
exactly.
Yeah, good. So now, but while in school, they should have taught you guys more of electricity. I enjoyed the electricity so much because if they play the show, you put the wire, then you take the reading immediately. You get so I don't know why. It's entirely fine anyway. I enjoyed the electricity. That's what I'm trying to say. And my school back then was not the best secondary school, but then you see experiments. Those guys did a lot. We were coming to school every Saturday. just to do experiments from my SS2 down to SS3, just experiments. And then I think I enjoyed that anyway. Now let's go about resistance now. When it comes to resistance, you talk about a good conductor and a poor conductor, and then an insulator. Like I mentioned earlier, if you are a good conductor, it means that your resistance is what? Your resistance is low. A poor conductor, resistance is high. All right. Now, I don't want, should I be writing these things, guys? What do you think? Like I'm crying already. A good conductor. Nobody's saying anything. Has low resistance. Because I'm writing for you people, nobody wants to say, oh, don't worry, don't write, just be talking. Titi and Mess and Co. Huh? Poor conductor. Because I think if you guys are writing, you guys should be like, oh, don't stress yourself again. Don't worry, just be teaching. All right? So a poor conductor has a high resistance. Everybody has bone. Has a very high resistance. All right. Now, very good insulators has infinite resistance, right? So it's very difficult. I am vexed. Just available for the knowledge today. You are vexed. What happened? What happened? Why are you vexed? Let me be a caring teacher today. What happened? Oh, yeah, send me your account number. If I say I know the verse will just go out immediately. But what's the year? Send the account number. No, so don't be vexed, okay? Do you know the funny thing is that your brain function better when you are happy. How many of you have noticed that before? Your brain function better when you are happy. Have you noticed that before? Yeah, it's function better. So don't be angry, okay? Be happy. After now we'll talk about that. Let me know what the challenge is. Right. Don't be vexed, okay? We dilute your verse in Jesus' name. We use ice water to dilute that verse. All right, you're fine. All right, so the next time is that is a very, very good insulators. Very good insulators, right? Has infinite resistance. So very good insulators has infinite resistance. They barely, all right? Then another good thing I want to let you know this evening, all right, is that silver is the best conducting material. Should in case the best conductor we have is silver, but because silver is expensive, we'll not make use of copper. After silver, the next best conducting material is copper. Because of how expensive silver is, we'll not make use of copper for virtually everything we do in electricity. Is that okay now? But silver is actually the best, but quite expensive. All right. So I will not give the reason here. I will just tell you that silver is the best conducting material. And I've said why I said so. Silver is the best conducting material. Is the best conducting material. All right. So that said, and I've given you why we now make use of copper in almost everything that we do. All right. That said, let's make progress. All right. So now some of the high resistance materials we can make, like your Constantan. How many of you have heard about Constantan wire that we make use of as our resistor? We use your Constantan. How many persons here? Nobody. So when we need high resistances, right? Okay, still said yes. When we need high resistance, right? If we need that, if they are needed in a circuit, right? If high resistances are needed in a circuit, we make use of the special alloys that they are like a Constantan, right? These are some of, there's one I call this Magnenta or something, right? A Manganin, Manganin, all right? You also have your chrome and the rest of them. So, but I think the basic ones are that your Constantan and your Manganin. I hear more of Constantan. So these are some of the materials that we make use of, right, as a high resistant material. When we need high resistance in our circuit, we make use of some of these special alloys. All right. So now that leads us to the Ohm's law. The Ohm's law is actually the law that verifies this resistance we're talking about. And it's simply that V is directly proportional to what? V proportional to your I, isn't it? We have that V is equal to what? IR, right? Where R is the what? Constant of what? Proportionality, right? So now it simply says that current passing through a metallic conductor is directly proportional, right? Current passing through a metallic conductor direct proportional to what? To the voltage across that very what? Circuit, or call it the PD between the what? The ends, all right? So that gives birth to the Ohm's law. I'm not going to give what the definition. I believe we all know what your Ohm's law is. So for the Ohm's law, we'll have that V is equal what? Your IR. All right. So remember that R is the proportionality constant and it depends. It was a challenge. What happened?
Nothing, sir. It was a mistake.
Oh, okay. Okay. So remember your R is the proportionality constant. So after today, I have no classes with you guys again. Oh, interesting. And it depends on the nature of the conductor. But if anyone invites me on time for their matric, I'm going to be there. Anyone that invites me on time, not 2 weeks to the date you are telling me, at least if you give me 2 months gap, right, I'm going to be there. It's something I'm going to take upon myself. I'm going to be there, provided you give me enough time, like 2 months gap, all right? So it depends on the nature of the material. And meanwhile, for the record, I like food. I don't want to hear story. Lillian will tell you. So it depends on the nature of the material. All right. I don't want to hear story. So food has finished, so please now. All right. So that's for your Ohm's law. Now that leads us to your resistor. Myself might not note a month to the matric. No, you should know. It's always on the calendar actually. So unless they move it. All right. So now the pieces of equipment that we use in your circuit is what we call the components. Anytime you hear components, we're talking about what? Some of those equipment that we use in your circuit is your component. One of them is a resistor, and the resistor now measures the resistance. Does that make sense now? Resistor measures what? The resistance. And there are two kinds of resistors. We have the variable resistor, which is an example of the variable resistor is your rheostat. All right. Example is what? Rheostat is one of them. Then we'll have the known resistor, which we can just make by making use of those wires I spoke about. Just getting a measured length of your constant time. That becomes your known resistor. We call it the standard resistor. But variable resistor are those ones that we can change, that can actually change the resistance through a circuit, right? Within a specific period of time. So these are the two kinds of resistors. The standard resistor, right, which is also known as the what? The known resistor. And your variable resistor example is your rheostat. All right. So now let's get started and then write some of these things down for your reference. So we'll have your resistors. Titi, you're writing tomorrow, right? Titi is writing tomorrow. And what was his name? Emmanuel. 17th. Emmanuel, you're writing tomorrow, right? Okay, 17th is on Friday. Chinoso. Okay. So who is not writing tomorrow? I think it's Paul. Rachel, okay. Hey, I need to give her a call. I should call her later tonight. Yeah, I should. All right. So all of those things that will connect in a circuit is what we regard as your what? As your components. All right. So and one of those components is your resistor, which measures what? Sorry, resistor measures the resistance. Then let's look at the two kinds. So resistance will give your resistor will give resistance to the circuit, right? And I mentioned there are two kinds of your resistors, right? So which are for the resistors, I mentioned two of them. I said we'll have the standard resistor, standard, and then we'll have the rheostat, which is a variable resistor. Rheostat, which happens to be a variable resistor. All right. So for this one, you can just get that from length of resistant wire, just from what length of resistant wire. Example is your constant time, right? Example is your constant time, right? Length of resistance wire. Just cut out the length and that gives you this guy. But for this guy, we use it to adjust the current flowing in the conductor, right? So flowing in the circuit, used to adjust current flowing in a conductor. All right, so that's for that. Now let's look at the connections of a resistor in series. A resistor is in series, you add them together. Remember what I said? If a resistor is in series, what happens to the voltage? What happens? Who can tell me? If resistors are in series, if you have a connection where the resistors are in series, what will happen to the voltage? All right. So resistors in series. This is a very powerful point we need to take note of, please. So if the resistor are in series, what happens, right? Let me see if I can draw the diagram basically. So let's have a sketch. V is shared. Beautiful. That's what I want to hear. I think your anger has gone away. Don't mind me, Charlie. Okay, the anger is still there. That would be a serious matter because you know. But I'm just trying to imagine how Meso's face looks like when she's angry anyway. It wouldn't be funny. I think people I know how their faces look like when they are angry. I think I've seen Emmanuel angry before. I think I've seen Lillian angry before. Right? Her own, yeah. Her own is a serious matter.
It's a lie.
I've seen you several. Look at this young lady.
It's a lie.
Don't worry, we're in public. I will not cast you now. Come to think of it, you and Emmanuel are the oldest persons I've known for a long time, actually. All right, I think yours is close to when you prepared for WAEC, isn't it? So what are you telling me? Then I'm brethren, the kind of stress I'm going through drawing these things, I don't think is worth it. What I'm just trying to say, if you have R1 here, this phase you guys are just the cramming phase. This is R2 and R3. All right, so let's assume that yes, now that's the phase you guys are currently. So I don't know why I'm stressing myself this much like this, trying to get the diagram. Because this is quite stressful actually. All I'm trying to say is that if they are in series, my circuit will not contain complete. All right, my people, I'm saying that if it's in series, what happens to your resistors in series? Let's say these are the voltage, like the values flowing through, right? That the voltage here is going to be shared like a meso said. So V will be equal to what? V1 plus V2 plus what? V3. All right, but your I1 will be equal to I2, which is equal to, sorry, your I rather. Or let's put in that the current flowing through here is your I. All right. Then let's say that here we'll have I1 right here, we'll have I2, we'll have I3. And for this place, we'll have the V, right? So let's have something here, we'll have V. So this is my V1, my V2, and this is my V3. So for connections in parallel, sorry, in series, your voltage will be shared like a measure said. Now, but for the current, I total will be equal to I1 equal to I2 equal to I3. All right. Now for your resistance, I how to get the resistors now is going to be that R is equal to R1 plus R2 plus R3. I can actually prove this from your Ohm's law, right? But that might not be necessary at the moment. We're running out of time. A lot of things I want to show you guys. All right. So that's for that. Okay, so in series, and I've told you guys why that current is going to be that way. So anytime in series, current is going to be constant because that is how the connection is meant to be. But for the voltage, it's going to be shared. But when it's in parallel, we'll expect the reverse to happen, right? We expect the reverse to happen, and that is why you see that when you connect different bulbs in series, if bulbs are connected in series, as you put more bulbs to the circuit, the dimmer it gets. Who can tell me the reason why it's getting dimmer? As you put in more, what happens? Anybody? Why would if I'm putting more bulbs in series, right? Why would the bulb get dimmer? Nobody? Why would the bulb get dimmer? Anybody talking? Should I call names? Paul, just enter. Let me give him some more time to breathe. Mesh, over to you. Anybody? I just said it here in the class now. Good. Resistance is increasing, isn't it? Right? And the voltage is shared among the bulbs. Are you seeing it now? So as it's increasing, right? If you add the resistance together, if they are in series, the resistance is combining, is increasing. R1 plus R2 plus R3 is increasing. And eventually the voltage is shared. And because of that, it gets what? It gets demand, right? And what does it tell you? Anybody? Sorry. Another key thing I want to add to what I said, right, is that remember that as the resistance is increasing, what happens to the flow of current? The flow of current is also reducing. Aside what Paul mentioned about the shared voltage, as the resistance is increasing, R1 plus R2, you are compiling the resistance, is keep increasing. So this is what we're going to what? Get dimmer. This is practical question that you can see at every point in time. All right, so let's look at the parallel now. If they're in parallel, I'm not going to draw that because of time, right? So now resistors in parallel. So because of time, I will fail to draw that, okay? Hope I'm permitted. but I think I should draw it, right? So now in parallel, what happens in parallel is that voltage stays the same, okay? Voltage stays same, all right? Current does what? Current is shared. Can you see what I'm writing? Because it looks as though I can't see it from my end. Okay. Okay, great. So how come I'm not seeing it from my end? What has happened? All right. So voltage is shared and current is as well. Current what is shared. All right. Current is shared. Now for the resistor, for your resistance, we're expecting to have that 1 over R will be equal to what? 1 over what? R1 plus 1 over what? R2 plus 1 over what? R3. All right. So that is exactly what will be expected of us to have in a parallel connection. All right. But who knows? Let me say this now. If they give you capacitance, okay, I know I will not be able to touch that. If capacitors are in series, you do this. Like capacitors are more like the opposite of resistors. Can you hear me now? I repeat again. Capacitors are more like the what? Opposite of what? Resistors. If capacitors are in parallel, you add them as if you are adding resistors in series. If they are in series, you now apply that of parallel to it. Does that make sense? Give me a thumbs up if that makes sense. All right, great. Student case. Now, we've spoken about what resistors, which is coming from one of the components. Remember what I said about your resistors, right? Because I want to say something very important. That the component designed to give resistance is your resistor, right? The component gives resistance. So now there are two kinds of resistance. You have an external resistance, which is coming from this component. You have internal resistance, which is coming from the cell, right? So two kinds of resistance. External resistance, which is actually what? From the components you are adding, just like your rheostat, just like your constant wire, right? When the presence of them in the circuit brings about that resistance. But your battery on its own has an internal resistance, which actually kinds of opposes or actually impedes the motion of current through the battery or through the cell. Let me call it the cell now. So that's the internal resistance, right? Is the one inherent in the cell itself. That's what we regard as the what? Internal resistance, right? Basically, it is offered by the electrolyte inside the cell. You know, you have your Daniel cell, Laclancha cell, right? You have your lead accumulator. I think it's either you studied that in chemistry or you studied in physics. Yeah, Leclanche cell, Daniel cell, lead accumulator, the one that has PB and the rest of them. So the electrolytes in those cells is what actually brings about the resistance, right, of the flow of current in those batteries, right? So now let me quickly put that down, which is your internal resistance. And so you read about those cells actually. Now, internal resistance of a cell. So for the internal resistance of a cell, it is important to know that the amount of the EMF that is delivered by a cell is not just dependent on the cell itself, it's also dependent on that internal resistance. So to save us time, I'll just make one statement here regarding internal resistance. I wish I had time to write everything down, right? And then we'll start explaining them one after the other. That would have been faster, and by now we should have been done. All right. So this is the resistance. This is the resistance offered by the electrolytes to the motion of current. All right. So number one, let me put it that way. Now, the second one, if the internal resistance is low, a large current is obtained from the battery. And it is denoted by small r. Remember, external resistor, capital R. Internal resistor, small r, right? It is always the resistor that they draw near to the cell. In case they draw the diagram, it is always close to the cell. That very R is always near to the cell, right? Now, if an external resistor is connected to a cell that has internal resistance R, this is now the formula that we'll make use of, all right? So now let me put your small r here to know that this is the symbol for your internal resistance. Internal resistance makes use of what? Small r. When do we make use of this formula? It is anytime you notice that a cell that has internal resistance R and there's an external resistor connected to that very circuit. This formula is what we use to do that, right? So if an external resistor, capital R, and I've explained what we have, it can be a standard resistor, it can be a variable resistor. An external resistor of resistance R, after now we'll solve questions, right, is connected. If it is connected in a circuit containing a source of EMF, E, then the current flowing will be, take note of this formula. I know back then I used this formula a lot during my own jam, right? So if you want to calculate that current flowing, it's going to be that I is equal to E all over what? Capital R plus what? R. And this is our second formula for the day, right? So this is the formula we use when we're looking for the current flowing through a circuit when it has an external resistor connected to a particular circuit that has a cell with an internal resistance small r. Is that okay? A thumbs up if you're following. So let me just label this my equation number 2, right? And then label the first one equation. I think there are a lot of equations here anyway. So why not? Let me just keep calm and keep it this way. All right. So now the next thing I want to talk about is your thermal PD, right? Thermal PD and your EMF. I've said EMF, I've said PD. So now, but from in the beginning of the class, I said something. Your thermal potential difference is that potential difference when the circuit is closed. When the circuit is closed, we make use of that very guy to be your potential difference. When the circuit is open, we'll have your normal EMF, all right, which is the what from a cell or from a battery. So these are the key difference between your PD, which is thermal PD V. We use V for your thermal PD, and then we use EMF, right, for just the electromotive force, which is your what your the PD for your battery as well. So these are two kinds of potential difference that we have: the terminal potential difference and what electromotive force. All right, these are two key PDs that we have. All right, so let me put them down: your thermal PD and EMF. Slash EMF. Number one, the thermal PD, terminal PD, not thermal, don't mind me. Terminal PD represented as V, right? Terminal, please. And these things are recorded though. Is the PD across cell when the cell remember what your PD is all about. We highlighted earlier that the potential difference is simply what? Is simply the work done in moving one coulomb of charge from one point to another, right? So now the terminal PD, right? Terminal, right? Yeah, terminal PDV is not the PD across the cell when the cell is delivering a current delivering a current right through an external circuit. So in this case, circuit is closed. Why the second guy, which is your EMF, right? Why your EMF in bracket E is the PD, the same thing when the cell is not delivering current, right, through an external circuit. Right, so this is what the PD for open circuits. All right, so next now we're going to look at the connection between the both of them. Is that okay? We're going to look at the connection between the closed your PD, your terminal PD, and your EMF, right? So EMF, when you're not delivering any currents, right? That's the energy stored in the battery. That's the electromotive force from the battery when it's not delivering. And then why the second one is when it is delivering. All right. So we're going to look at the relationship between the two. We're going to look at that shortly. So now let's look at that relationship and we're going to connect it to what we have regarding our V's and our I. All right. So that said, what's the relationship between those two guys? So I think I should put it here now. I will not derive anything, but I think we should do that. All right. So recall that I is equal to what? E all over what? R plus small r. Remember where this one is coming from. I'm trying to change this internet actually. It's lagging. And I have to disconnect to connect. 2 sec. All right. I don't know if you can still hear me, but if you can hear me, um, let me proceed. Well, can you hear me, please? I can't see anybody, so someone might need to turn on their voice, their mic, and say yes if you can hear me. Can you hear me?
Yes, you can hear you.
Okay. All right. Okay. All right. So now the second part of things is your what do you call it? Sorry, I think two mics are on. Am I still sharing my screen?
Can you
Can
still
you
see
still
my
see my
screen?
screen? Okay, okay. I think you can. All right. So now the next one, this is coming from when there's a connection between your E, right, and the internal resistance R and the capital R. Also remember from Ohm's law. Remember this is what? Relationship between what? Internal resistance. Internal resistance slash your external resistance. Now, from your Ohm's law, we know that V is equal to IR. So that I is also equal to what? V all over R. Still making reference to the same current. Current when there's resistance, internal resistance. Current when there's no internal resistance. All right. So both of them are still equal. So we have that E, but you don't have to care about this derivation, men and brethren. Just should in case you forget. Right? So is equal to what? R plus R is equal to what? V all over what? R. Are we together now? Hope you are seeing what is happening there. All right. Or instead of bringing this guy, let me just pause it right here, not to confuse anybody. Right. Let's take it off from here. Good. Now, from equation 1, I will have that E is equal to I open bracket R plus R. I will follow you now. Now, what else do I have here? We have that E is equal to IR plus R. So that E is equal to what? This is V, right? V plus R. Are we making any mistake? E over 1. Then this is my V plus IR, please. Plus IR. Now, if I want to make my voltage subject to formula, we'll have that V will be equal to what? E minus what? IR. So this is the relationship between your terminal voltage, terminal potential difference, and your EMF. All right. Relationship between what? Terminal potential difference and your EMF, right? At every point in time. Okay. So this is what? Relationship, right? Between terminal PD in bracket V and your EMF F. EMF E. Right. So that's it. Now, a group of cells, I'll not write down, I'll just say it. A group of cells is called a battery. A group of cells is called what? A battery. Group of cells called a battery. So I don't give you so much information. All right. Now, the next one we're going to look at is your resistivity. Remember, I've given you key formulas. First one is the relationship between your resistance now, external resistance, and your internal resistance. Now, this one here is about being in parallels and being in series. Okay, being in parallel and being in series. And then the last one now has to do with what the two kinds of potential difference that we have: the terminal PD when the circuit is delivering current, and when the circuit is not delivering current. All right, what am I saying? When the cell is delivering current to the circuit, and when the cell is not delivering current to the circuit. So the two of them, there's a connection between them. All right. So that said, let's look at resistivity now, right? Resistivity of a wire, right? Now it's dependent on two key things. It depends on the length of the wire and the area of the wire, right? Resistivity of a wire, the ability of a wire to resist the flow of current is dependent on two things: the length of the wire and the area of the wire. Now, the bigger the area, the higher the resistance. Sorry, the bigger the area, the smaller the resistance, because more can flow through. Now, the longer the wire, right, the more the resistance. That is why in your power bank, the cord is usually short. Maximum respect to every short person in the house. I don't think we have any short person in the house, right? So now, that's why the cord for your power bank is usually very short. I don't think there's any short person in the house. I think I've seen Paul. I've seen there's nobody, right? So now, for Nikki Good Silver, it seems today was her fashion week, right? I took time this week to actually view some status this weekend. I think maybe I don't know. I don't really know. Do you actually went for a competition? At some point, I was like, are you still writing the jump? Oh my goodness. All right. So I was saying something about the resistance of a wire, right? The resistivity, right? Depending on the length. So short power bank means of a short cord, because the shorter the cord, the smaller the lower the resistance and more current can flow through. And if you check something, all those cord that their wire is too long, sometimes it takes a longer time for your cord to get filled, right? Because what? The longer the wire, the higher the resistance and the lower the current that will flow through it, right? So I'm going to give you the formula straight up for that one. So for that very one, we'll have your resistivity. You know, all of these things are under your resistance now, right? So I've spoken about current. I spoke about potential difference. We're now pitching our tent under resistivity now. And that's the says that what? Resistivity of a wire is directly proportional to the length of the wire and inversely proportional to the area of the wire. All right. Now, the resistance of a wire is directly proportional to the length of the wire and inversely proportional to the area of the wire. That's the resistance of a wire. Now, the resistance of a wire, if we represent it very well, you now use this symbol for the resistivity, for the constant of proportionality, then L all over A, what? A. All right. So resistance, the resistance of a wire is dependent on two key things. It depends on the length, and also it depends on the length, and then it also depends on the area. These are two key things. It depends on the length and then the area. All right. So now it's important to know that your this guy, every year they ask this. If you check your past question, am I correct, guys? For those that have actually gone through and seen anyone that has to say something about that. So now A equal to the area of the wire. Oh, have you seen that before? Area of wire is equal to pi d squared all over 4. So that this our formula can now be changed to good. Will now be changed to, you can write that the resistance will be equal to 4, the resistivity, the length of wire, all over what? Pi d squared. So anyone you can remember is good to go. But I think it's important you take note of the area of the wire. The area of a wire, we take it to be pi d squared. Right? So I've introduced how what your resistance is dependent on. Resistance of a material is dependent on the wire of a wire, depends on the length of the wire. It also depends on what again? Depends on what do you call it? The area of the wire, right? Good. Now, there's something else I would have spoken about, but if I see that in past questions, then I'll make reference to that. Something about how to calculate, if you have the particular number of battery, effective resistance, the effective potential difference when they are in series and when they are in parallel, right? So, but before I look into that, let me ensure that there is something along that. So, measurements of resistance, measurements for resistance. Measurements of resistance. There are different instruments we can use to measure resistance. One of them is the Wheatstone bridge, right? One of them is the Wheatstone bridge. Now, at this point, we're not looking at the principle behind it. You just have to know how to apply it, all right? So now for the Wheatstone bridge, one of them, it has to do with ratio, and they will draw it for you. They always draw that Wheatstone bridge that looks like this. How many of you have seen this before? It has my diagram is looking like what a mess of 3. How many of you have seen something like this? Your Wheatstone bridge along these sections, right? How many persons? Something that looks like this might not be really perfect this way, right? But then it now has your galvanometer at the center right here, right? Let me just have space to draw my galvanometer right here at the center, right? It has your symbol this way. So that one just works with a ratio, right? The Wheatstone bridge. That's why you're laughing. Nick, you will see, but when are you writing your own exam? Can you hear me? "17th. It seems you are prepared so much. You get the kind, okay, let me not talk. Let me not talk. Is this, at some point, I said, is this young lady writing this down? Later, you will show me the way, I'll show us the way, how you can actually gain that very confidence. All right, so that's the Wheatstone bridge. The next one is the meter bridge, right? This meter bridge, I can remember solving a question back in 2017 on this, right? Yeah. Show us where, Mama. Mama, where they pamper. She's a very wealthy woman. Oh. She has money. All right. So now, for this Wheatstone bridge, is a way of measuring the resistance, right? Now, the unknown resistance will be on the left-hand side, while the known resistance is going to be on the right-hand side. And there will be a changes in the length along the wire, right? So now we're going to have 100 minus L. All these things I'm saying, that I'm just going straight to give you guys formula because some person's head now, just give me formula Madewaka, right? So, and that's what we're doing now. So now, this X is the one you are looking for. Anytime they are measuring resistance, right, using the meter bridge, X is the what? The resistance you are looking for. R is the given resistance. L is the given length. This 100 is because the uniform wire that is used for this meter bridge is 100 cm in length, right? So, but they always give you the L, or sometimes they might ask you to look for it. We're going to solve questions on that, so you see how the questions look like, right? So now, you have that the X is equal to the unknown resistance, which is usually on the left-hand side. Unknown resistance always towards the left. Then we'll have the R, which is the given resistance. All right, L is the length. Now, the next one I want to speak about, we're going to solve examples on this. Paul, please bring it on, please. We'll have the potentiometer, potentiometer. You sent to the group already. All right, beautiful.
Yes, sir.
Beautiful. Do you have anyone on Wheatstone bridge? Sorry, anyone on what do you call it? That meter bridge.
I think meter bridge is there. Shoot.
Is there, right?
Yes, sir.
Okay. So we use potentiometer to compare the EMF of two cells. If you are comparing the EMF of two cells, we make use of the what? The potentiometer. What did I say? comparing the EMF of two cells, we make use of what? Potentiometer, right? Comparing, used for comparing so we have E1 all over E2 is equal to L1 over L2. You know what the L is already now? It's the length, okay? So these are the key formulas we'll be making use of as long as these questions are consigned. All right, so let's see how to get our hands dirty using all of those things. All right, so Paul, let's move. 2 seconds, let me quickly return it. Someone's, there's an emergency I need to respond to through this call. Why I import some of this? Another person supporting B. Meso said B, all right? 3 resistors will have 2 these are connected in series. A 6V battery is connected to either end of the combination. Calculate the potential difference between the end of the 250 resistor. Now, can someone unmute and tell us what you did? Very fast, please. Very fast. Anyone? Paul, do you have the same answer as them?
I have not finished solving.
Paul, what are you solving?
I left the. I wasn't with my phone for some minutes. So
Okay.
I just
So please, next time when this kind of thing happens, just call the attention of anybody, right? I thought I muted I needed to assist someone. I thought I muted myself, you know. So Titi, over to you. Who wants to explain? I think Meso, your mic is better. Titi's phone is making a lot of noise. I don't know.
No, not. I promise.
Titi, I cannot hear you.
I said I will not make. I mean, my microphone will not make lots of noise today.
Oh, yeah, go ahead. Go ahead. Explain.
Okay. So
Yeah.
to find the R, like the total resistance, I did
Okay.
250 plus 500, and then
Okay.
they said 1 kilo ohm, I guess. So
Okay.
that kilo will be
Yes.
1000. So I
1000
did
ohms.
250
Okay.
plus 500 plus 1000. My answer was
Good.
1750.
Good.
Then I now went ahead to find my current, and I think the
Okay.
current to be the potential difference
Okay.
over the R total. So I
Yeah,
did
the R total. Yes.
6 divided by 1750. Then my answer
Correct.
was 0.00343.
Okay.
Then I went
Makes
back to that
sense.
formula that says V is equals to IR.
IR.
And
Makes
then
sense.
since they asked us to find the potential difference between the end of 250 resistor, I
Yes.
did
Yes.
V is equals to 0.00343 times 250. And then
Makes
V is
sense.
equals to 0.86
I don't
ohm.
know whether the value is correct, but your steps make sense. You understand what I'm saying now? That's the step to take. I've not solved myself to know whether those actual values you are calling, whether it is what it should be, right? But if a person agrees that that's the value, that means you are correct because the step is amazing, right? Okay, so now the key things you mentioned here, they are in series, right? The connections are in series. So because they are in series, what happens? The voltage is what is shared. Is that okay? Voltage is what is shared. Now, there's something she did, which is quite amazing, right? And why she did that is because if the voltage is shared, it means that the current is constant. Did you see that now? Now, the current is what? Is constant. So because that current is constant, that's why she did what she did, right? So now she had to get what? R total. And R total, she added everything like she said. Because of time, I don't know if I will do this. 500, right? Plus 1000, right? So RT is equal to, call that your values now. So, but the key thing here is that the voltage is shared. the current is constant because they are in series. Can you call that your value now? The total this thing you have 1,500 plus this is 1,750, isn't it? 1,750,
sir.
right? Now we know that V. Since we have this now, right? We're looking at the battery is 6V, all right, which means that the V total is equal to 6. Let's get I total. So I total is going to be V equal to IR divided both side by R, right? So that it means that it's going to give us V total over what? R total. So we can get our total current. With that total current, all right, we know that the total current will be equal to what? I1 will be equal to I2 will be equal to I3, isn't it? For the resistors, the three of them. And that's why she now said any I total she got, she now has that the V250, right? Is that not so? Yeah, V250 for that resistor will now be equal to what? I total, are we together? Multiply by what? I total multiply by what? Multiply by what? The resistor 250, right? So anything you get, I think, what was the answer? Yeah, 250. So what was the final answer you guys got? All right. So we have that V250 will now be equal to what? What was the current you guys got here? What was the value here? 1750. Sorry. This is 6 divided by 1750. All right. I hope that you are following. So this is 6 all over 1750 multiplied by 250. All right. So someone get that value. Hope we understand what happened. So V for 250 is equal to what? What's the answer, guys? Call the value. Call the value for me. Somebody should talk now. We don't have the whole time in the whole world, please.
0.86.
Yeah, so everybody will agree for 0.86. So that is it. The concept we applied here is the fact that it is shared, all right? So once voltage is shared, we know what happens. If current is not shared, which is constant, that's why we're able to do this. Because I know that once I get my I total, right? One thing I should have written here, yeah, like I said that, right? Which means that I250 is also equal, right? I total is equal to I3, right? Which is our I250. Very, very expedient. All right. So the next one, it says that 3 cells, right? 3 cells each of EMF 1.5 and internal resistance 1.0 are connected in parallel across an internal resistance of 2/3. Calculate the value of the current in the resistor. You've seen that they have their internal resistance, right? About 3 of them, and they are connected in parallel, right? And then they are asking us to find the value of the current. Remember the formula, right? That each time I have external resistance and I have internal resistance, they are actually connected by a specific formula that says that I is equal to E, isn't it? All over what? R plus what? Small r. Are we together? Give me a thumbs up if you know why I'm using that formula. A thumbs up if you know why we are using that formula. Good. Now, how many cells do we have there? We have 3 cells, isn't it? And each of them has an EMF of what? Of 1.4, and internal resistance of what? Of 1.0. Now, they've given us our big R, which is our what? 2/3. The only business you have right here is to what? To get the total effective internal resistance of the battery. Since each of them is 1.5 volts, and the internal resistance for each of them is 1.0. So anytime you see internal resistance and you also see external resistance, this formula should come to your head, right? Now, there's a statement I wanted to make before for you guys when you have internal resistance and external resistance. Sorry, internal resistance for more than one cell. That's what I said before, that if I see that question, I'm going to add it for you guys. And eventually the question has surfaced. So there's a statement I made, right, which I said I should have added for you people for that very place regarding the battery. Now, something I jotted down here when I was preparing the note for you guys regarding that battery, right? Let me quickly get that, okay? So I wrote something down. I said, for your battery, that place I said for battery now, right? So let me write it down. For your battery now, That will enable you solve that question. I never knew I was going to see it. I just said if eventually I was thinking it's not important, but I know I read it out. It was in your textbook. That statement was there. All right, but you've seen that they ask question along that side as well. All right, so group of cells, it says that group of cells connected together is called a battery. It's called a battery. All right, so the next thing I have here is that if n identical cells of EMF E and internal resistance R are connected in series. So if you have these cells connected in series, what will be the effective EMF? All right, now one, I wrote here, okay, if n identical cells of EMF E and internal resistance R are connected in series, if they are connected in series, right? Look at the statement now. If they are connected in series, let me underline that series. If they are connected in series, one, we'll have that the effective EMF for the number of how many they are, if there are 15 of them, the effective EMF will be equal to N multiplied by E. Does it make sense now? So if I have 15 cells and they told me that these 15 cells, that the E for each of them, that the EMF for each of them is 5, it means that the effective EMF is going to be what? That number of cells times by the EMF. Does it make sense now? That's if the connections are in series. But for that question they gave us, connections are in parallel. We're going to see what happens if they're in parallel. But should in case it's a series, multiply that number of cells by that EMF they gave us. If you understand what I'm saying, give me a thumbs up. Give me a thumbs up if you understand what I'm saying. Beautiful. And only you, Nikigo Silva, and the rest. How about you? Now, 2, the effective internal resistance. All right. Effective internal resistance will also be equal to what? N times by what? R. Remember that your R is your what? Internal resistance. Hope is making sense. So this is what we make use of if they are in series. No matter how many they are, you make use of that. If they are in series, this will give us what we need right here. All right. But if they are now in parallel, that was one thing I said. If you remember when I started, I said I'm going to either add it or not if I see it in your question, because I thought I've given a lot of information. But since they need it here, if they are in parallel, right, effective EMF, for me, I think the textbook they use mostly for this is this senior secondary school. The effective EMF will just be equal to E, right? That is for one cell. You're not going to multiply by how many they are if they're in parallel. Is that okay? It's just going to be what? E, right? So for all. Is that okay now? You're not multiplying what? That. It remains what? It stays the same. Are we together, guys? It stays what? It stays the same. All right? So now the second one is now your effective resistance. The effective resistance, remember small r, when they are in parallel, effective resistance will now be equal to E, sorry, not E, R divided by N. Are we together, brethren? Do you understand what happens here now? Everybody, does it make sense now? when they are in parallel. For those cells, when they're in parallel, what happens? When they are in series, what happens? All right. I think with this, I've given you all you need. What I omitted before, I've given you all you need on that, right? So effective resistance and the effective EMF. Now, for that very question, you could observe something right here that they've given us. There are 3 of them, right? And because they are connected in parallel, what means that what? Effective resistance will just be equal to E, right? Is equal to E. Now, sorry, not effective resistance, effective EMF is equal to E, right? So now the next one is your effective resistance. That's internal resistance. So effective resistance, and that's why I'm using the small letter here, will now be equal to what? Your small r divided by your what? Your n. All right. That said, they said they have about one of them, 3 of them. So it means that E is equal to 1.5. Small r, internal effective resistance now, right? Let's call it E effective resistance will now be equal to what? There are 3 of them and they have internal of 1, which means 1/3. Do you know why it is 1/3? Give me a thumbs up because n is equal to 3. A thumbs up if you know why it is that. All right. So now, the next thing we need to do now is to get the current. So we have that I, the current, is equal to EMF is E all over. We have small r 1/3 plus our big R, which is our external resistance. External resistance is 2/3, right? We have external resistance to be 2/3. This is 2/3. So therefore, we have that I is equal to 1.5 is the same thing as what? 3/2, isn't it? Am I correct? 1.5 same thing as 3/2. Good. So we'll have 3. I'm doing that because in case your calculator is not there. So this is 3/2 divided by 1/3 plus 2/3. They have the same denominator, so we can add them together. So this is 3/2, then bring them all together. That will give us what? All over what? 3/3. So that internal resistance is equal to what? 3/2 divided by 1, because this will cancel out. All right. Then you could see what will happen there, that your I will now be equal to what? Times, you invert the same thing. So it's going to be 3/2, isn't it? 1/1. All right. So 3/2, do we have the option right there? Yeah. So that will give us that I is 1.5. So I is 1.5A. Any question, guys? Hope it makes sense, guys. Does it make sense? Everybody, a thumbs up if it does. Yes. Anybody that has a question? All right. So that is what we have right here. Okay. So this is 1.5 right here. Now, the next question here says the same thing. 3 cells, each of EMF 1.5 and an internal resistance of 1.0 are connected in parallel across a load of resistance 12.65. Calculate the current in the load. The same process. Okay, is that okay, Yakubu? Is that okay? Okay, Paul, your hands are up. Yeah, Paul, go ahead.
Sir, I don't really understand this that effective EMF and resistance.
Okay. So Paul, look at what I'm saying, right? Is that if the connections are in parallel, you understand this formula, right? You get this formula, right? Yeah, just turn your mic, let's discuss. So I can actually give me feedback in braille. You get the formula, right? So now, the effective EMF now, good. Effective EMF, you have 3 cells. Remember what I told you? That a group of cells is called a battery. Group of cells called a battery. Now, if you have 3 cells and the connections, the cells are in parallel, the one that is effective, more like your R total, your E total is going to just be what? That value 1.5. Do you get the point now?
Yes, sir.
It's going to be that particular value, which is what? 1.5 V. right? So it's going to be what? The same. So for parallel, the effective EMF is just for one of them, right? So one of them, that will be your E. So let me make that statement very well for you right there.
So
This
what
is
of
for
in
one of
series?
them. You said?
What is in series?
I can't hear you.
No, okay. I'm asking what of series? In series.
For series, good. For series, that's what we have here now. If it is for series now, the effective resistance is going to be the number of resistance multiplied by 3. If they're in series. Confidence, your video is on in case you don't know. All right. So now, for effective resistance, for the effective EMF for series now, the number of cells you have multiplied by E. Confidence, can you mute yourself, please?
Yeah.
Good. Number of cells multiplied by the E for one of them. E for one of them. Remember, they're identical. Look at the statement I made here. If N identical, if the cells are identical, all right? So now, if they are in series, the number they are multiplied by one of the EMF. Because the EMF are the same, they're identical if they are in series. Then effective internal resistance will now be the number of cells multiplied by the internal resistance of one of them. You get the point now. So now, but if they're in parallel, the effective EMF is just the EMF of one of them. Are you seeing it now? EMF of one of them. So that means this E, let me write, where E and R are the EMF and internal resistance of one of them. I hope that makes sense now, of one of them, right? So that's how we now solve that particular problem they gave us here. Because for this problem, they've mentioned something that those guys are in parallel. Because they are in parallel, we just pick only one of them. That's our effective EMF. Then for our effective internal resistance, it's going to be what? The internal resistance of one of them, which is 1.0, divided by how many they are. And then we'll apply our formula and get our answers accordingly. All right, so this is the same question repeated, right? So we'll have 3H of 1.5 and internal resistance of 1.0 connected in parallel across a load of 2.6. We should calculate the current in the load. The same process. Is that okay? Give me a thumbs up. They're in parallel. So it's the same thing that I did in the other question we're going to do right here. Anybody confused? All right, same process. Guys, I have to go at this point. This one is what? I have a class at 6:15. Sorry, 16:15. That's 4:15. All right. So this is resistance of 4-meter uniform wire of cross-sectional area. This is this. All right. What is the resistivity of the material? Remember the formula I gave you? That R is equal to what? 4. We'll have this. We'll have this. We'll have pi d squared. All right. But I think the end of reason this one, just use that R is equal to this all over the area. They've given us the area. They've given us your resistance. So this one, R is equal to 0.425. All right. The length of the wire, uniform, yes, resistance of 5 meter. Yeah, length is 5 meter. All right. You're now looking for this resistivity. So just plug them in and get your answer. The area has been given to you 0.2 times 10⁻⁻6. Plug it in and get your answer. All right. A thumbs up if you understand what I say right here. So this one says, find the work done in moving a 2C charge between 2 points X and Y in an electric field if the potential difference is 100 volts, right? The work done in moving a 2C charge between 2 points X and Y in the electric field if the potential difference is 100 volts. What did I tell us about potential difference? I said earlier that potential difference is simply also known as your what? As the work done, isn't it? Right. Now, but they gave us charge. I'm thinking how best we could connect this together now. So now, current is what? Quantity of charge over T. If they are between 2 points, I'm moving the charge 2C. If the potential, we find the work done moving a 2C charge. Remember that potential difference between 2 points is the work done in moving one charge from one point to another. Does it make sense now? From one point to another. Now, if they're saying 2C charge, it means that it takes one charge, 100 volts. Does it make sense now? It will take how many charges now? One charge, 100 volts. So now 2 will not be what? That's how you're going to solve that question. 2 will not be what? So I think this is coming from that definition I gave you guys about your potential difference. Any question, Paul? Remember, potential difference, I think I defined it here. I think I defined it. I said potential difference between 2 points is the work done in a circuit when one coulomb of charge moves from one point to another. So now, moving 1 point, they said that the PD of the circuit is 100 volts. So what happens if we now move 2 PD, like we move 2 charge of the circuit, all right? The answer is just there, moving at you, all right? So I think I've answered that particular question using that definition, right? If potential difference is 100 volts, so for 1C is equal to 100. So for 2C will now be equal to 200. So that will be what? 200 joules. All right. Any question on this? You can also make use of that formula that work done is equal to QV. But for me, my solution here was coming from our definition. And I think that is one key thing you have to remember. Or you can make use of this. This is the quantity of charge. This is the volt. Anyone that works for you is entirely fine. All right, guys. So please, I might need to step out at this point. So sorry, I couldn't have the time to. Electric current of 2 ampere. This is your I, right? They gave us the resistance, determine the heat, heat produced. You are linking this to your energy. Meso is amusing you. Also, I'm using Meso. All right. So determine the heat produced. They give us resistance. They give us your current. You have to link this to your power, right, and energy. Right. So if you read your electrical energy, it's just 4 pages. I think I will just snap that place and send. Senior secondary school is amazing, right? So let me check that particular electric energy. So how many pages? 1, 2, 3, 4, 5. Oh boy. 6, 7. It's a little bit bigger. But I believe you guys can read it. If you can read that, then you are done with electricity entirely. You can read the electricity. And even the wiring, which color do we use for wiring? I answered that question in 2017. They will tell you which one is the earth, which one is. I'm going to snap it and send to you guys. Just find time. Just take 1 hour to go through it. That's the last thing: electrical energy and power. I have a class at exactly 4:15. Okay, look at this one. In a meter bridge experiment, 2 resistor, 2 pi, and 3 ohms. Sorry, 2 ohms and 2 occupy the left and the right. So remember that if they say the left, this is the left, this is the right. So the one that is the left should be on top. That left and right is what will tell you what you are doing. Remember, you have X over L equal to, I've said these things before. L over R equal to, can I remember the formula again? You have L all over 100 minus L. So the one at the left hand side is this. 2 is here, 3 is here. Go ahead and now find the balance point. All right. Then for this up one, like I said, apply you have the current already, I. You have the resistance. You have the time. We know that P is equal to IVT. Right. So they gave us I. They gave us time. You can get your V, right? V is equal to IR. Then plug it in here to get the heat. Is that okay? So it's just direct. Anybody confused in what I just said? Anybody confused? Give me a thumbs up if you understand what I did here. V equal to IVT, V equal to I. Can't you hear me? Yeah. So just, it's very direct, okay? Yeah, very direct, okay? So guys, at this juncture, let me not delay another person's class because, and the person has 0 tolerance, has a resistance of 90 ohms on that voltage B. Just go ahead, all right? Just go ahead. This one is to resolve it. Total resistance. It is important to know that these guys, these ones are in series. They are in series, all right? They are in series, and it's going to end up being this way when you add everything together. 2 plus 2 plus 2 plus 3, right? Are they in series? Yes. 2 plus 2 plus 3 plus 2. This is 2, 4, 6. This is 9. All of them will now come together to look like this. You now have 9 here, and those 9 are still in series with these ones. Do you agree with me? Do you agree with me? Series, all those guys series, then you still have another series right there. So this is 9, 10, 11. So your answer here should be 11. All right. That's resolving them in series and in parallel. All right. If the maximum voltage across 100, find the maximum power. You can use two things here. Maximum, they gave us resistor and they gave us the voltage. We know that P is equal to V squared over R, isn't it? You can use this formula. Also have that P is equal to IV. These are different formulas. Where P is equal to I squared R. I think these are some of those power formulas. There are about 4 of them. Please go check it out so that on the judgment day, you will not open your eyes and be sweating when there is fan and when there is AC. We'll call it internal heat. May it not be your portion in Jesus' name. All right. So they said the terminal voltage of a battery is this and supplying a current. Look at this one right here now. You guys are laughing. All right. So this one says that internal voltage of a battery is 4 when supplying a current of 2. And this, when supplying a current of this, the internal resistance of the battery is what? Remember what I gave you? First of all, you have to get V, use that relationship. V is equal to E minus what? IR. All right. So apply this to get your answer. Also remember you have that E is equal to R plus R. All right. So use this to get the actual value that you need. 2 of them can actually deliver the answer to you. All right. So all the best, guys. I need to move at this point. This is also the same question, right? Find the balance point Z. I think we've solved it already. Find the balance point, X of length, this, the same process. So this is my last class with you guys. And I'm so excited that it is coming to an end. But then my prayers are with all of you. And I know that you guys are going to do well. I still apologize for what happened in between the class. You guys should have told me and I would have muted myself. I needed to assist someone with something. And that's what I went to do without knowing that my mic was on. And these people were just busy listening to what was happening without saying, oh, can you mute yourself? The headset was on my ears, but I never knew. All right, guys. So I need to move at this point because the person will be waiting. I know he must have dropped a message. Today is what? 12th, 15th, yeah. So they must be waiting. All right, so all the best, guys. Those writing on 17th, on Friday, I'm going to call you tomorrow evening, and I'm going to call each of you 3 minutes. I will spend 3 minutes on the call. Paul, when are you writing?
Saturday.
Saturday, all right? So let me write down. Our Paul is on Saturday. Sorry, 2 sec before I leave you guys. Paul, Saturday. Who again? Writing on Saturday. Okay, Meso, Saturday. Paul, Saturday. Meso, Saturday. Who is writing tomorrow? Rachel. Friday, Thursday. Then Titi says Friday, right? Nikki, when are you writing? Confidence. Friday, okay. How about Nikki? I can't remember what she said. Same. What do you mean by same? There's a lot of same there. Friday is there. Friday. All right. So all the best, guys. Let me go and give to the other guys as well. Maximum respect, everyone. See you when I see you. I would have said if you guys can turn your camera, let me take a screenshot. But then I know that some of you are inside there where I don't know at the moment. Maybe if some of you are in the market even, collecting money. People like Nikki collecting money, so she cannot even turn her camera on. That's entirely fine. All right. So all the best, guys. My prayers and my wishes are with you guys. I wish I had more time, but because it's clashing with a class and I need to run at the moment. All the best, guys. I love you all, and I wish you the very best. Our efforts is going to pay off. Akuna Matata. All right. Peace out.